Okay, guys, so this is our last section for chapter 3. It's L'Hopital's rule. Right. So it's going to take us way back to the first chapter where we're taking limits. It's an alternate way to find the limits of some of these um, functions that have indeterminate form, right? So L'Hopital's rule can be used to find limits of these indeterminate forms, right? 0 over 0, infinity over infinity, 0 times infinity, 1 raised to infinity, 0 raised to the 0, and infinity raised to the 0, right? So here's the theorem, and it says that suppose that g and f are differentiable functions on an open interval containing a, except possibly at a itself, right? And suppose that the limit as x approaches f of x equals 0 and the limit as x approaches a of g of x equals 0, or both the limits go to infinity, right? If the limit as x approaches a of the derivative of x over the derivative of g exists, or if this limit is positive or negative infinity, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of the derivative of f over the derivative of g, right? And so this holds true for one-sided limits or limits as x goes to infinity as well. So what does this mean? It basically means that if you're taking the limit of something that's in that indeterminate form 0 over 0 or infinity over infinity, you can take the derivative of the numerator, take the derivative of the denominator, and evaluate that limit. And sometimes that limit is easier to evaluate, right? Be careful, though. You don't want to use the quotient rule, right? You're not finding the derivative of that whole function. You're finding the derivative of its numerator and the derivative of its denominator separately. All right, so let's take a look at a couple examples. So we did this one actually in class, the end of class on Tuesday. But if you remember this limit, the limit as x approaches 0 of sine of x over x, we spent a lot of time proving that that limit was 1, right? That's when we introduced the squeezing theorem. We found those two functions, right, that squeezed this function between those two things. So we spent a lot of time to figure out that our limit for this was equal to 1. But this is someplace where we could try L'Hopital's rule to find the limit. So the first thing you want to do is make sure that it's an indeterminate form, right? So if we take our limit here, right, the limit of the numerator, right, as x goes to 0 of sine of x over the limit as x goes to 0 of x, right? The limit as x goes to 0 of sine of 0 is 0. And the limit as x approaches 0 of x is, of course, 0, right? So there's that indeterminate form that we need, right? So it fits that the theorem, that part of the theorem, that we've got a limit where you end up with 0 over 0, that indeterminate form. So what we're going to do now is we're going to differentiate the numerator and the denominator separately. So L'Hopital's rule basically says that this limit is going to be the same as the limit as x approaches 0 of the derivative of the numerator. So we're going to take the derivative of sine of x over the derivative of the denominator. So the derivative of the denominator, right, that's the derivative of x. So when we take our derivatives now, we've got the limit as x goes to 0. The derivative of sine of x is cosine of x. The derivative of x is just 1. And when we take this limit, right, you just end up with cosine of 0, which is 1. So that's it. So first you make sure that it's an indeterminate form of 0 over 0, infinity over infinity. If it is, take the derivative of the numerator, right, and then the derivative of the denominator, and take that limit. And if it works, you found your limit. Now that, think of how difficult it was when we used the squeezing theorem to figure out what that limit was, to prove that that limit was equal to 1. With L'Hopital's, it's really pretty straightforward. But again, don't make the mistake of taking the derivative of that whole thing. It's a derivative of the numerator and the derivative of the denominator separately. We're definitely not using the quotient rule for this. All right, so let's try maybe a couple more examples. So here we've got the limit as x approaches 0 from the right of 1 minus the natural log of x over e to the 1 over x, right? So first let's check and make sure that this is going to be in indeterminate form. So the limit as x approaches 0 from the right is going to be 1 minus, if you remember our graph for the natural log of x, it looks something like this, right? So when you take the limit as x approaches 0 from the right, you're coming down along here, right? It's going to positive infinity. So it's going to be, I'm sorry, negative infinity. So it's going to be 1 minus negative infinity. That's our limit for the numerator. For the denominator, as x goes to 0 from the right, 1 over x goes to infinity. So we get e to the infinity, which is infinity. So we end up with 1 plus infinity all over infinity, and that's infinity over infinity, right? So definitely it fits the theorem, right? We can apply L'Hopital's because we've got it in this indeterminate form, infinity over infinity. Okay, so we're going to apply L'Hopital's. So if we apply L'Hopital's, right, we're going to take the limit as x approaches 0 from the right of the derivative of the numerator, so the derivative of 1 minus the natural log of x, all over the derivative of the denominator, which is e to the 1 over x. Okay, so we get the limit as x goes to 0 from the right. The derivative of 0, the derivative of 1 is 0. The derivative of minus ln over x is minus 1 over x. Okay, so there's our numerator. For our denominator, right, the derivative of e to the 1 over x, we're going to have to use the chain rule. So the derivative of e to the 1 over x is e to the 1 over x, right, times the derivative of 1 over x. And I guess I could have done that in my head since I'm running out of space, but here we're going to get the limit as x goes to 0 from the right. It's going to be negative 1 over x. That's in the numerator. The denominator, the derivative of 1 over x is negative 1 over x squared, so we're going to end up with negative e to the 1 over x all over x squared. You can think of this as dividing fractions, right? So I'm going to write this as, let's see, negative 1 over x times negative x squared over e to the 1 over x. And let's see what happens with that. We're going to end up with, I'm going to have to squeeze this a little bit. Let's see, I'm going to go down to the next, well, let's do this. The limit as x goes to 0 from the right, it's going to be a positive x over e to the 1 over x. And the numerator goes to 0. The denominator goes to infinity, but that's just 0, right? So think about how difficult finding that limit would be without L'Hopital's rule. You know, what would we do? We'd have this indeterminate form, infinity over infinity. There's nothing really algebraic you can do, but L'Hopital's gives us this wonderful and basically pretty easy way to find our derivative for that. Okay, so let's see. You could pause here if you want, try a couple problems, but I'm going to go on to maybe